Hello everyone, I am back, Mr. Heim, and today we're looking at 322, which is a little bit of what you saw last lesson, but this is good, used for a good emphasis on it, on which method to use. Now, in this video, I am also going to go over a mistake I said in the last video, and that's probably the most important thing here in this video. But here we go. So recall two things before we get into this: the power rule, in which the power rule states for a polynomial function f of x equals a times x to the n, the derivative of x, the slope function, also known as the derivative which we talked about last video, can be defined as a times n to the x to the n minus 1. Where we multiply those two in front and then subtract the power there. And that's great. And then the other thing we learned what a derivative was. So recall that a derivative is aka the slope function, or the slope of the tangent lines, or we can think about it as the IROC at all given moments. What's that? And what that is the limit as h approaches 0 of f of x plus h minus f of x over h, which again, how do you find the slope at a given moment? Now for any given point x, what you do is that this part right here is the slope between 2 points x comma f of x and a point that's h away, x plus h, so a little bit to its right. And what we do with these 2 points is we're finding the slope between 2 points, but this limit right here is minimizing the distance between the 2 points to 0. So basically, if you keep finding the slope between 2 points, well, as that distance between them minimizes to 0, well, the slope between the 2 points will look just like the slope at that one given point. Now, that's what we talked about last video, but let's talk about my correction that I made, a correction I need to make. Okay. Now, last video, in 3.2.1, I said the following. I said, if f is continuous, then f prime of x exists. Now I'm going to introduce some words for you. In other words, the derivative exists, but the better way to say it is we say that f is differentiable. And that word differentiable comes from we can look at its change in differences. That's why we talk about the finite differences, is like the slope. So f is differentiable is just another way of saying f prime of exists. The slope function exists, or think about it as like we can take the derivative of f of x. So IROC exists, all of that stuff exists. Now my mistake here is that that's not a true statement. This is not true. And the reason for that is f does not have to be continuous to be able to take the derivative. All right, here's a counterexample. And say we look at, and this is a function we actually looked at previously, the absolute value of x. We look at the absolute value of x, f of x is continuous. The limit exists. Remember the three properties of continuity is that the limit exists at all points, the function exists at all points, and the limit and the function will equal each other at every given point. But f prime of 0 does not exist. The slope at 0, the instantaneous rate of change at 0, does not exist here. And the reason for that is, remember that f at x equals 0 is a corner. In which case, at a corner, on f prime of x, the slope at x equals 0 can be a lot of different things. Can equal many different, instead of saying things, let's use numbers, which implies that it does not exist. Right? We have a positive slope that's constant, but at that corner at 0, the slope of the tangent line can be so many different possibilities. You can have a horizontal line, diagonal line there, diagonal line there. In fact, there's infinitely many slopes at 0, which infinitely many does not mean to exist. So the slope at 0 does not exist. In other words, what all this is saying, it's my puppy, is that f does not need to be continuous for it to be differentiable. In fact, it's the other way around. If f is differentiable, which i.e. f prime of x, the derivative exists, i.e. There's a instant rate of change exists for all x. All right, so if f is differentiable, the derivative exists, the instant rate of change exists for all x, then f is continuous. So it's the other way around. We're not necessarily going to get into that now, but you can understand from its definition, remember that f prime of x, the definition of the derivative is the limit as h approaches 0 between 2 points. Well, if you can take the limit between 2 points, well, then f has to be continuous because the limit will exist and the function will exist where that limit exists. So there it is. So that's my correction, is it's the other way around. Not if f is continuous, f is differentiable. That's false, as we can see with the absolute value. But if f is differentiable, if we can take the derivative, then we know that f is continuous. Okay. So that's my correction. Now let's get into some of the examples for this lesson to help you with it. I'm going to push this paper away. So example number 1, example 1. Let's say we have a function f of x, which is equal to negative 5x squared plus 3x. And I want to find the slope at the instantaneous rate of change at, say, 1. Now, there's 2 methods you can take. So approach 1, which is the power rule, because this is a polynomial here. So then we can do f prime of x, the derivative of f of x will be negative 10x plus 3. So again, that's the derivative of f of x, the derivative of f of x, or you can think about it as the slope function of f of x. Saying the same thing, but I want you to understand what that word derivative means. So if we want to find f prime of 1, we plug in 1 and we'll just get negative 7. So again, what that's saying is, so the slope of f of x at x equals 1 is negative 7. And just like that, we got the answer. The power rule is great. What a shortcut. That was so quick. But this only works sometimes. It does not work every single time. The approach you can always use, if you remember what I've been saying in math, is the definition of the derivative, which is the limit as h approaches 0 of f of x plus h minus f of x over h. And I write that a lot because it's so important, and I want you to be like, oh, you're writing it again? Yes, I hope you understand, you memorized that. And this works all the time. So yeah, you have a shortcut in the power rule, and that's great, but it's not always going to work. And you want to always have a backup in case this doesn't work, or maybe you want to check your answer. Right? Now let's do it in this example and see if we get the same thing. So we have f prime of x will equal the limit as h approaches 0 of, we plug in x plus h, we have negative 5x plus h squared plus 3x plus h minus negative 5x squared plus 3x. Notice I do parentheses around each thing here, the f of x plus h and the f of x. It just helps me make less algebra mistakes and my experience of teaching this when tutoring students is that it also limits their mistakes. Now, if we simplify this, you'd have negative 5x squared, and that you'd have a 2xh there. So at the negative 5, you'd have a negative 10xh, and then you have a minus 5h squared plus 3x plus 3h plus 5x squared minus 3x. We distribute that negative over all over h. So then we have the derivative of f of x is the limit as h approaches 0 of, that will cancel with that. The 3x will cancel with the negative 3x, and that's it. Notice that they all have h, so I'm going to factor out an h right away. I have negative 10x minus 5h plus 3 all over h. Those go to 1. So we have f prime of x is going to equal the limit as h approaches 0 of negative 10x minus 5h plus 3, in which now we can evaluate that limit by plugging in 0, and what you'll get here is the derivative of f of x is equal to negative 10x, that'll go to 0 plus 3, which, look at that, it's the same thing we got with the power rule. So we know we did it correctly, in which f prime of 1, you plug it in, you also get negative 7. Right. So 2 approaches, one always works, one sometimes works. It's important you know both, but it's important you know the definition of the derivative, because we're going to learn there's certain situations where power rule doesn't work, which this will be where you have to take. Right. But if you can use the power rule, use the power rule. What a tool. It's awesome. All right, let's look at example 2. Now, example 2, I'm doing this because there's problems that you're going to see, and I'm not sure if you're going to be able to necessarily tackle this type of problem. So say we have the limit as h approaches 0 of, and I wrote this down, x plus h to the third plus 2. Oh, I'm sorry, not x plus h. Let's do 1 plus h to the third plus 2 minus 3 over h. So if you see that in the question said, okay, what's f of x and what's f prime of x? Okay. So looking at this, I can see the definition where that 1 plus h to the third plus 2, this is going to have to be the f of x plus h. And this right here will have to be the f of x that they're minusing. Okay. Now look inside. Look inside. That's usually the goal with these, and we're going to be, there's going to be something else with that in the future. But if you look inside here, notice that the x plus h, I don't see x's, so they must have already plugged in a number. There's a value at which they want to approach, which that's probably 1, because you have the x plus h word. There's a 1 there. So I'm thinking that what this function is f of x is equal to x to the third plus 2, because remember, they had to plug x plus h into here, so this was the original x, in which you have to the third plus 2, and I think what they did is they wanted f prime of 1, in which when they plugged in 1, let's see what happened. Was this f of x? Well, if you plug in 1 here, 1 to the third is 1, 1 plus 2 is 3, and that's great, because there's the minus 3, right? Because remember, it's f of x plus h minus f of x. So good. So now we know the function. Now what's f prime of x? Yes, you could do this with the definition of derivative. I'm not going to. I'm going to use the power rule here and get 3x squared by the power rule. All right. And there you go. So at 1, if they wanted to know what the function was at 1, because they could simplify this if they wanted to, but with the power rule, we already know what the slope function is, so by plugging in 1, we'll get 3. So the slope of the tangent line of f of x at x equals 1 is 3. Okay, there you go. Say we took it one step farther really quick, and it said, what's the equation of the tangent line of f of x at x equals, say, 1? All right. Well, we know to write the equation, it's going to be y equals m times x minus x1 plus y1. That's point slope form. Well, we know what the slope is of f of x, right? We know that the slope is 3. We just found that. The instantaneous rate of change at 1 is 3. Now, what point is it? Well, we're looking at x equals 1, so you always have to plug 1 back into f of x, the original function, because again, we want of f of x. So f of 1 is equal to, if you look back here, 1/3 is 1, plus 2 is 3. So we're at 1, 3. So then we can use that point with the slope to write the equation, which is y is equal to 3x minus 1 plus 3. And that's the equation of the tangent line of f of x at x equals 1. Just make sure you find your second point, the 1, 3, by plugging into f of x, not the slope function, because we want to know where the function was located at that particular moment, and then what's the rate of change at that particular moment, which that's why we need the derivative. So I hope that helps. My correction, I talked about if f is differentiable, if you can take the derivative of a function, then f is continuous, not the other way around. And then we looked at some examples where we can see that if you can use the power rule, use the power rule. What a blessing. But the definition of the derivative is the bigger blessing, because if all else fails, we have something that will always work. All right. Hope that helps. Good luck.